All right, I'm going to do pretty much this whole worksheet except for the two check your understanding pages, I think. We'll see. Okay, so for each of the following scenarios, first answer each part on your own, then compare your answer. Okay, no. Okay, so scenario one. Oops. Okay, an ant crawls directly away from the base of a vertical pole that is 3 feet tall. Okay, the ant is crawling at a rate of 1 foot per minute. Okay, so here, so you'll almost always draw a picture, and you can see there's pictures down there for number 4, but let's do it without that. Here, let me put a picture right here. All right, when you're drawing, just try to do simple stuff. You know, when they talk about an ant, make that a point, you know. When they talk about a vertical pole, you know, just a line, you know, try to keep things as simple as possible. Okay, and then this is 3 feet tall. So anything that's not changing, you can label with a number. If the thing's changing, my advice is label it with a variable, and it'll save on a couple possible mistakes that could be made. All right, and then this is the base, you know, down below, and then the ant's moving away from there. Okay, the ant is crawling at a rate of 1 feet per second. Assume d is the distance from the ant to the base of the pole. Okay, so let's say the ant is here. Okay, so d is this distance. This distance here. Okay, as the ant walks, just notice that d increases. Right, as the ant goes this way, this distance is going to increase. So that rate of change, once we come to it, will be positive. Okay, assume d is the distance. Okay, and h is the distance from the ant to the top of the pole. From the ant to the top of the pole, I call that h. Okay. All right, then we can already see like number 4. We can already see B is going to be the drawing. So let me see. Okay, what's the value of the rate of change in the scenario? Okay, the only rate of change that we know of is the rate of change of this distance d as the ant goes this way, because the fact that the ant is crawling at 1 foot per minute, that means this distance d is increasing at 1 foot per minute. And so that's what we know. And always good to put everything in kind of these math symbols. So here you'll do dd dt. Okay, how this is the rate of change of that distance divided by the rate of change of time. Okay, and that's the rate. And that's the rate that we're looking at. They say this is 1 foot per minute. Okay, normally you're just going to put 1. They say to include units, so we will, but normally you'll just worry about units at the end, I think. Okay, how tall is the pole in this scenario? Okay, pole is 3 feet. Okay, how do you know that this scenario can be represented with a diagram of a right triangle? I don't know, there's no good answer for this one exactly, except, you know, just their description. Vertical pole, so that's vertical. And then the ant is going with the ground. So, you know, if you have a vertical thing with the ground, then there's a natural right angle here. So then these two are right angles. And then the fact that you have some kind of distance that was mentioned from the top of the pole to the ant, that kind of gives you the hypotenuse of that right triangle. But basically the answer to that question is just it kind of naturally happens from the description of that scenario. All right, and we already got 4. Okay, and then the last one, select which equation appropriately represents the relationship between the quantities in the problem. Okay, so Okay, so it's definitely not going to be equation B. Can't be equation B because this involves some other variable A. They kind of introduced another variable that we're not interested in. So I mean, you want as few variables as possible. You don't want to be introducing new variables kind of unnecessarily. All right, and then the other ones are just, which one's the Pythagorean theorem that we're going to use, which one's like the correct Pythagorean theorem. And for us, with this drawing, the hypotenuse is h, so that gets squared by itself. Okay, so this equation C. Okay, so that appropriately represents the relationship between the quantities in the problem. Okay, they say at a certain time, and any of these related rate problems, they always happen at a specific moment in time. So at a certain time, the ant is 4 feet away from the base of the pole. Okay, let me redraw this. Oops. Okay, notice, even though they said the ant is 4 feet away, don't label this 4, right? So you only want to label things with numbers if they're not changing. So that's why I labeled the pole as 3, since it's not changing. Okay, the ant is 4 feet away, and so what you do with this, instead of labeling that 4, just write at a certain moment d equals 4. Okay, what is h at that time? Okay, the time when d is 4, this will be a 3, 4, 5 triangle. You could do Pythagorean theorem. H at that time is going to be 5. Okay, find d and h 2 minutes after the time mentioned in question 6. Okay, so let's find d first. So, okay, in question 6, they're 4 feet away. And then remember that the ant was traveling at 2 feet per minute. Okay, so at a certain time it was 4 feet. And then if it goes 2 feet per minute, then in 2 minutes it's going to go another 2 feet. So this will be 6 feet altogether. Okay. Okay, so after 2 minutes, 2 more minutes. The bottom d is 6. Okay, and then to find h, that's that whoops, I almost passed it. Just do Pythagorean theorem. And that's h. Okay, so notice how with these problems, I think one thing that there's a lot of reasons that I think make this difficult, but one reason is you just you're gonna have to be doing a lot of algebra and geometry in these pre-cal. So these are hard. Like these are problems that are kind of incorporating kind of everything that you've learned in the last 4 or 5 years, kind of all into one problem. So all right, so just something to get used to with these. Okay, so scenario 2. An oil spill in the shape of a circle is expanding on the surface of a pond. Okay, the radius of the oil spill is r, and the area of the oil spill is a. Suppose that at a certain time, the area of the oil spill is 30 centimeters per second. And keep in mind it's expanding, so that's just at some time it is 30 square centimeters. Okay, and the radius of the spill is increasing at 0.2 centimeters per second. All right, label the diagrams so that it shows the spill, labeling the area A and the radius of the spill R. Okay. So just labeling, they're just kind of getting you used to this idea that you're going to be either drawing pictures or given pictures, almost every problem, and you're going to have to be labeling your pictures each time, you know. So, all right, so this will be R. What did this say? Okay. That's R, that's the radius, and I guess this is the area here. Okay. I guess that's all. All right, so they're just step by step going. Okay, that was the labeling. Okay, so select which equation appropriately represents the relationship between the quantities in the problem. Okay, since it's a circle and since it talked about area, oops. Okay. So these two deal with area and radius, but just this equation's not right. This 2 pi r is really circumference, so they just used a wrong formula, so we can't use that. And then this, I don't know if you remember, this is volume of a sphere. So they're just giving you wrong formulas. So this is the formula we'll use since we're dealing with a circle, and that's the area of a circle formula. All right. Okay, what's the rate of change given in this scenario, and what variable is changing? Okay, so they said the rate of change that's given is the rate of change of the radius. So they say the radius is increasing at 0.2. Actually, let me check that real quick. Okay, so here I put this, I grabbed this from the problem, so because we'll need this. Okay, what's the rate of change in this scenario? Second. Okay, the radius, they say radius of the spill is increasing at 0.2 centimeters per second. Rate of change given, and what's variable is changing. Okay, so the rate of change given is 0.2 centimeters per second. And what variable is changing in that case? The radius. Okay, what is R at the certain time given in the scenario? Okay, so let's see. Okay, so they say at the certain time, they don't give us what R is, but they do give us what A is. I think, yeah. So the area at the certain time is 30. So sometimes they don't just give it to you. Sometimes you got to solve for it. Like in this case, they tell you the area, which we know is pi r squared. At the certain time is R is 30. And so we'll have to solve this for R. So okay, so that would be R at that time. Okay, next one. If the rate of change of R continues to be 0.2 centimeters per second, what is A after 3 more seconds? Okay, so in 3 seconds, the radius will increase by 0.6, right? If it increases at 0.2 per second, it'll be 0.6 after 3 seconds. Okay, so now the new radius would be plus, what was it, 0.6? 0.2 centimeters per second, yeah. Oh, wait. Oh, they tell you there. 3 more seconds, so yeah, 0.6. Yeah, 3 3 seconds at 0.2 per second. Yeah. Okay, so that's the new radius. Looks weird, but whatever. What is A after 3%? Okay, that's the radius, so then we just square that and times by pi. So that we'd probably do in a calculator. Pi r squared. Okay, suppose the spill is expanding so that its area is increasing at a constant rate of 0.4 square centimeters per second. At a certain time, the area is 50. What is r at that time? And then what are a and r 10 seconds later? Okay, suppose the spill is expanding, so the area is increasing. Okay, at a certain time, the area is 50. Okay, what is r at that time? Okay, so if the area, pi r squared, and at a certain time, that's 50. What is r at that time? Solve for r. What are a and r 10 seconds later? Okay, so 10 seconds later, let's find a first. That'll be easier if we have how area is changing. So in 10 seconds, if it increases 0.4 square centimeters per second, it'll increase 4 centimeters in 10 seconds. 4 square centimeters. So the area in 10 seconds. The area would be 54. Okay, so just it started at 50. Yeah, added 4 square centimeters. Okay, and then we'll just if this is the area, we already know the formula for radius, so we can solve for that then. So if area is, again, pi r squared, and that equals 54, we can say this is okay. Okay, so that's all 10 seconds later. Okay, so the next one talks about the original scenario. And they made just a little mistake that doesn't really matter actually, but they had a 3 cubed. That should be 3 squared because this comes from Pythagorean theorem. So okay, they describe the same scenario. So here I'm going to draw a picture that represents that scenario real quick. And we'll talk about it. Here, let me put it down here. There's the pole. Okay, there's the distance from the ant to the base of the pole. And that's the distance from the ant to the top of the pole. Okay, also, we know that the ant is crawling at 1 foot per minute, so that distance d is changing with time at 1 foot per second, or 1 foot per minute. Okay, and then at some point in the problem, they talk about this. So they say, if we pick up here, differentiating both sides of the original equation that we got from Pythagorean theorem. So this original equation is an equation that relates the values of the original variables. When you differentiate and you get this gives you the relationship between the rates of change of the variables and I guess the variables also. Okay, and that's why I guess they called it a rate of change equation because it just involves rates of change. Okay, and then let's look at how they got this equation based on the original. Okay, so when you take the derivative of h squared, you do power rule. So bring out the 2, h to the 1, so that's 2h. But you always get, you have to take the derivative of the inside. So the derivative of the inside in this case is h. You know, it's almost like this is in parentheses. H is the inside. And then the derivative, every time you come to a variable that's changing with time, and you take the derivative with respect to time, you know, that dt, you have to do d, that variable dt. You know, so you have dh dt. Okay, and the derivative 3 squared is 0, and then the derivative d squared is the same idea as h squared, 2d dt. Okay, then they say, assume that at a certain time the ant is 4 feet away from the base of the pole, and then they ask us what's h and dh dt. Okay, another little mistake that they made. If this is a capital H, this has to be a capital H. There's no, you know, if you want a variable to represent the same thing, then they have to be the exact same variable. You can't change it. Okay, so let's find those. All right, so they say at a certain time, the ant is 4 feet away from the base. So at a certain time, d is 4. And if d is 4 at that time, and the pole is 3, this will be a 3, 4, 5 triangle. That means h would be 5. All right, and if they ask for dh dt, so I used the original equation to find h, but now to find dh dt, we'll have to use this rate of change equation, since that expression shows up there. Okay, so just substitute everything that we know. So 2h, so 2 times h is 5 times dh dt equals 0 plus 2 times d, 4 times d dt, and d dt was 1. Okay, and then just solve for dh dt, and we'll simplify that to 4/5. Okay, and in this case, any kind of rate of change is they're all gonna have the same units. All right, those are the two answers to that. Okay, which of the following represents the rate at which the ant is crawling away from the pole with respect to time? Okay, that's d dt. So when the ant's crawling away, just kind of naturally, a consequence of this ant going this way is this distance changing, this distance increasing. So the rate of change of the ant is the same as the rate of change of this distance. They mean the same thing. Okay, which of the following variables can we now replace with the value of 4? I guess d is 4. So, weird question. Okay, and then these down below, there's a certain reason why I want to skip this. I understand what they're doing, but it's going to be maybe misleading if you focus on this too much. So I'm going to just kind of skip this. I don't know. Okay, which of the following equations appropriately represents the scenario when the ant is 4 feet away from the base of the pole? Recall that in scenario 1 of the previous activity, at the certain time, the right triangle being considered is a 3, 4, 5 triangle. Okay, so we already know the original equation was h squared equals 3 squared. Okay, when we take derivative, 2h dt equals 0 plus 2d dt. Okay, you could see you could cancel those 2's out, but it doesn't matter. All right, and then which equation represents that? So when the ant is 4 feet away, so when the ant is 4 feet away, that means D is 4. Okay, and that means at that same instant, that was a 3, 4, 5 triangle, so H was 5. And so we know we need to plug in 5 for H and 4 for D. 5 for H, 5 for H, and 4 for D, so that's A. Okay, now solve. When the ant is 4 feet from the base of the pole, what are the values of H and DHDT? Oh, we already got those up there. Oh, I didn't realize that they weren't really asking us. They were just previewing, getting at this. Okay, my bad. Okay, so let's do that now then in case, yeah, just to do it. Okay, so what are values of H and DHDT? So we already got H is 5 from Pythagorean theorem. And here, I'll just write it here. So do 2 times 5 times DHDT equals 2 times D, which was 4. DDDT was 1. And then we solve this. All right, so now we're going to do like a full-on problem. Okay, so 2 cars, and they take a step-by-step, pretty much how you'll actually do these on your own once you start doing them on your own. Okay, 2 cars leave Central Square. So the 2 cars leave the same point. Okay, the first car drives north at 35 miles per hour, and its distance to Central Square is A. Here, A is actually a function of time because it's changing. Okay, the second car drives east at 50 miles per hour, and its distance from Central Square is B, and it's also a function of time because it's changing with time. Okay, the distance between the 2 cars is D. Okay, at a certain time, A is 20 and B is 40. Okay, sketch the general picture of what the cars and Central Square look like. Be sure to label the diagram with A, B, and D representing the distances mentioned in the stem of the problem. Okay, so let's say this is Central Square. Okay, car drives north. Do that. And the distance is A. Another car drives east. And they say the distance is B. And then the distance between the 2 cars, they say is D. Okay, and we know it's a right triangle because north and east are right angles, like make right angles. So, okay, be sure to live. Okay, that's it for now. Okay, notice they said A was 20 and B was 40, so you don't label your drawing with values of a variable that's changing. A is changing, so you don't put what A is at a certain time. You don't label that. Just put that off to the side. Okay, give a general formula for D in terms of A and B. Since we have a right triangle and we want to involve all 3 variables, that's Pythagorean theorem. So, okay, find a formula for D prime. So we'll just take the derivative of this. Okay, the derivative of D with respect to time in terms of A prime, B, and B prime. Okay, just keep in mind, different notation. A prime, same thing as dA dt in this context. B prime, same thing as dB dt in this context. Sometimes A prime and B prime will be dA dx or dB dx, so you have to use context to tell. Okay, and when they say find the formula for D prime, we'll solve for D prime. All right, so now we'll just take the derivative of this. And keep in mind, in this scenario, there's no fixed distances here. All these distances are changing, right? This is a car that's moving this way, so A is changing. The other car here is moving this way, so B is increasing. And as these increase, this distance between them gets bigger, and that increases. So all of these are changing. So when we take the derivative of these, they won't be 0. All right, so derivative of this, 2D, do power rule, it'll be 2D. And then the derivative of the inside with respect to time, you'll write dd dt. And that's going to be the same thing for all these. 2a dt. Okay, and then notice those 2's, we could cancel all those out. Oh, sorry, let me do it how they asked us to. Times d prime, prime, b prime. Okay, and then we'll solve this for d prime. And then divide by 2d. Okay, again, we could cancel out all those 2's, but okay. Are the two cars getting closer or farther away from each other at a certain time? At the certain time? Definitely getting farther away. So that as these cars go this way, this distance is kind of increasing as those get away. So are the two cars getting farther away, closer, farther away? They're getting farther away. And how fast is the distance between them changing at that time? Okay, real important to figure out what they're asking for in math symbols like dv dt or dx dt, or what are they asking for? Okay, find how fast is the distance between them. So the distance between them is d. That's the distance between them. So if we want to know what that's changing, we want to know dd dt. So we want to find out, or d prime. Okay, so that's what they're asking for here. Okay, so that's how fast is, okay, so that's what we'll solve for right now. Okay, so let's go up here and label everything we know. Just kind of write down everything we know, kind of organizing it. Okay, first car drives 35 miles an hour north. So that means as this car goes 35 miles an hour, this distance changes at that rate. So D, or A prime, is 35. Same idea, B prime is 50. I tell you the car is moving 50 miles per hour east. Okay, and then we also know at the moment in time, A is 20 and B is 40. Okay, so we just substitute that all into this formula for D prime that we're looking for. Okay, so I'll do that down here. B is 40, B prime is 50, over 2 times D. Oh, we gotta solve for D. Okay, so notice we have A and B, but we don't have D. We'll just solve for it real quick. So 20 squared plus 40 squared equals D squared. Equals 1600 plus 400,000. D is square root of 2000, which is 20 root 5, I think. Okay, so we'll put that down here for D, 20 root 5. All right, and that's it. So, you know, just get used to, you're going to be doing this all the time, figuring out what all the variables represent, maybe having to solve for one or more of them, and then substituting them into some formula to get the answer. All right, just to make that easier, I'll cancel those 2's out, divide everything by 20. Okay, so 135. All right, and then that will be, what was that, feet per minute, I think? Oh, wait, no, this is miles per hour. Okay. Okay, so last thing in the video, the next thing is to check your understanding. So I'll let people do that. Try that. Okay, so let's do this one together. An annulus is a region in a plane bounded by two circles with the same center, concentric circles. Okay, suppose S is an annulus with an inner circle of radius r and an outer circle of radius big R, little r and big R. The radii are changing so that r is increasing at 7 centimeters per second and big R is increasing at 3 centimeters per second. Okay, at a certain time, 9 a.m., they give you the radiuses of each. Okay, so sketch a picture. Okay, so let's do that first. So concentric circles, so they share the same center. Okay, and then one radius, kind of this outer radius, call R, big R, and then the inner radius we'll call little r. Okay, and I think the annulus is like all this area, like a little donut, 2D donut kind of thing, I think. Okay, be sure to label the annulus. Okay, representing the two. Okay, we did that. Okay, write a formula for P, the total perimeter of the region S. Okay, the formula should involve r, little r and big R. Okay, so let's do that. All right, so the actual so the actual figure is like this figure here. Let me try this. No, it doesn't work. Okay, there we go. Okay, and then the actual annulus is like just this part of it, right? So the perimeter of that is really just the circumferences of each circle added together, the two circles added together, I think. Yeah, perimeter is kind of just the, you know, this and this kind of the boundaries, the outer boundaries of the figure. That's the distance around, so that's the distance they're talking about, I guess. All right, I guess that's it. All right, what is P at 9 a.m.? Okay, oh, let's write a formula for P. So formula for P equals the circumference of the inner one plus the circumference of the outer one. Okay, just keep in mind, circumference is 2 pi r. Okay, so yeah, what is P at 9 a.m.? So at 9 a.m., little r was 30 and big R was 80. at 9 a.m. d equals 2 pi times little r was 30 and big R was 80. Okay, that's 60 plus 160 pi centimeters per second. Okay, write a formula for P prime, the rate of change of the total perimeter. Okay. Okay, since the radiuses are changing, radii are changing, the perimeter will be changing. Okay, but that should be a P. I don't know why that's a D. Oh, whoops, that just got erased. Oh, there should be a P here. And then, yeah, that should be a P. And then that should be a P also. I just made a mistake, I guess. Okay, for P prime, we're going to take the derivative of this equation with P. Okay, so we'll just go one term by one term at a time. So derivative P is P prime. Okay, when you do a derivative of a constant times the variable, so 2 pi is the constant, so we'll just rewrite it. And then derivative of little r is little r prime. And then the same idea, 2 pi big R prime. Okay, so that's the formula that they asked for. Okay, what is P prime at 9 a.m.? Okay, include appropriate units with your answer. Okay, so let's go back. So in order to get P prime, we need R prime, or we need little r prime and big R prime. So we need to know how fast each one of these are changing. That's what little r prime is how fast the little radius is changing, and big R prime is how fast the big radius is changing. So they tell us each one of those. So R, little r, is increasing at 7 centimeters per second. And then they say the other one is increasing at 3 centimeters per second. Okay. Oh, one's going to catch up to the other, I guess. It's weird. Okay. All right, and then, I'm using the different notation, so let me use the notation they ask for. Okay, not wrong, but they just want us to use a certain notation. Okay, now we just substitute it. Okay, R prime is 7. Big R prime is 3. 14 and 6, 20 pi. Okay. Oh, what am I doing? Okay, here, sorry. Let me finish this. Okay, this is centimeters per second. And hopefully you caught my mistake. Okay, this is just perimeter. This is not a change in perimeter. So perimeter, units for perimeter are just centimeters, not centimeters per second. Okay, so hopefully y'all caught that. Okay, write a formula for A. So So last thing they say, is the total perimeter increasing or decreasing? Okay, since this is positive, since the rate of change of the perimeter, since that's positive, that means this is increasing. Okay, write a formula for A, the area of region S. Okay, to get that area, we'll do like the area of the bigger circle and then subtract the area of the smaller circle. Okay, so the total area, okay, the formula should involve R, okay. So technically it's the two areas minus, so area, we know, is pi r squared for a circle. So it's going to be pi and then little r squared plus pi big R squared. Oh, that's not right. What am I talking about? So they asked for the area between them. So that's the bigger circle area minus the little circle area. Okay, if you want, you can pull out a pi, but it doesn't matter. Okay. Okay, what is A? What's the area at 9 a.m.? Okay, so the area is pi times, so at 9 a.m. the bigger radius was 80 and the lower one was 30, I think. Yeah. So 80 minus 30. Okay, so 64 minus 9. Wait, 60, wait, 70, wait. Yeah, 64 minus 9. 55. Is that right? 6400 minus 900. Yeah, okay. Okay, and then units, the distance was centimeters, so this will be square centimeters. Okay, write a formula for A prime, the rate of change of the area of region S. Okay, period. Okay, so that means we're going to have to take derivative. Okay, so we'll take derivative of this area formula up here. I'm going to take the derivative of this version here. Okay, area is, okay, if you have a constant that's multiplied, just rewrite the constant. Okay, the derivative r squared, we'll use power rule and chain rule. So 2r, we get power rule, and then dr dt, that's from the chain rule. And then same idea for the other one, 2r from, that's what we get from power rule, and then we get dr dt. I keep forgetting the notation. They want us to use the primes, sorry. Okay, what is A at 9 a.m.? So at 9 a.m., we have all this information. So at 9 a.m., they tell us little r is 30, big R is 80. Little r is increasing at 7, so little r prime is 7. Big R is increasing at 3. Big R prime is 3. All right, and just notice that that's everything, that's all the variables that we'll need to substitute to get A prime. That should be a, this should be a prime here also. Okay, so just substitute everything. Okay, big R is 80, R prime is 3. Okay, little r is 30, R prime is 7. Okay, so that would be 480 minus 420. 480 minus 420. Okay, so I guess that's 60 pi. Okay, and then that's centimeters squared per whatever unit of time they're using. Get seconds. Alright, so it's like a full problem. Did a couple at the end. Okay, so try those two check your understanding ones, and we'll go over those two in class on Wednesday.